University of Austin, Texas, in Austin, half of the time at the University of British Columbia, with Frank Chokri. Then he did his first PhD at the University of Illinois with, the first postdoc at the University of Illinois with Charles Cumming, and the second one with Julian Collins in the Johns Hopkins University. And now he's at the third one as a research associate in the Rochester Institute of Technology. He's going to talk about magnetized accretion rate in a minor black holes.
Thanks. Yeah, so this is a large collaborative effort that involves three schools, and pretty much me and Julian are the disk guys, and then the others in blue are the gravity experts, and Nico especially is an expert in post-Newtonian theory. So we're bringing all these different expertises together to do this calculation. So yeah, so what you see here is a snapshot of the surface density of the disk. I'll show you in the future later in the talk. So motivation, why study circumbinary disks? Well, it gives us a good example of if we observe coincident electromagnetic emission and gravitational radiation, we can do a lot of things. We can explore, we can get a new distance redshift measurement, and if we identify spectral lines for instance in the electromagnetic emission, we can also constrain the parameters of the system better, and constrain parameters of the disk, also of the binary in a more good fashion. And it can also help some sort of LISA type detector localize these things. So, LISA is on a cutting block, but there are other proposed observatories, and a typical LISA type telescope would have a field of view of the Hubble ultra-deep field, and so there are a lot of galaxies in here. So if we can use high cadence observations, electromagnetic observations of this field of view, then we can maybe identify a variable signal to that of a circumbinary disk, then we can help localize the source of the sky. And so kind of a prime expectation for these calculations is to see if there are characteristic variable signals from these disks that we can use to locate these types of objects. And they can help constrain merger rates. If we just look in the sky and see electromagnetic signals from these objects, we can constrain supermassive black hole merger rates. And it can be used to tell us about the evolution of supermassive black holes and their life neighborhoods, and also galaxy interactions and evolutions. Plus, it's also a prime example of a very unique laboratory to investigate plasma physics in a very dynamical gravitational field, and that's very exciting in and of itself. So so I hope I don't need more motivation than that. So that's my only motivational slide. I know
we're motivated.
Okay, great. So the general idea is you have galaxies, you have nuclei. These galaxies merge, and then nuclei settle to the centers of the gravitational well, and they do this in different ways depending upon the gas content or the stellar content. Stellar distributions can, through dynamical friction, relax the system and shrink the binary. This is a binary, black hole binary or nuclear distance versus time. And so depending upon the content of the system, you can get quick mergers or slower mergers. Zoom in on one of these simulations, you see that there are nuclei that are pretty close to each other. And this is a simulation by happenings at all. Do we actually see these things in nature? We see a few that are relatively close, but not as close as we'd like them to be. One example is 0.02 plus 379, which is very close. It's 5 parsecs, close relative to other similar systems. And they're resolved by radio observations, and they're very close together. And it's also the vicinity in Z of these objects highlights the fact that we're kind of at the limit of spatially resolving these objects with current technology. So we need improved telescopes to resolve the closer objects. And so even at this distance, I think the merger time is at the order of 10 to the 8 years. So still quite a while until this particular system would actually a potentially more interesting object is OJ287, which is thought to be a very supermassive black hole being orbited by a still supermassive black hole. And the model for the system is contentious, but one interpretation of the data which shows 12-year variability or spikes in the flux is that there's this black hole that penetrates the well, it's just a disk around the primary, and the secondary penetrates the primary's disk multiple times, and it creates variability in the accretion rate, which then creates variability in the flux radiation that we see from this object, which is a laser belief. And so we're actually looking down the barrel of this jet. So the accretion rate varies the flux things. And they predicted a delay in the flux, or actually it happened 20 days before the 12-year anniversary of the flare, and that is consistent with 2.5 p.m. Approximations of the binary orbit. So if these two objects are close enough that actually post-Newtonian effects change the orbit of the system, and those effects are consistent with the 20-day.
How did you get such a precise measurement of M1?
I forgot how they comes from that model. Is it the model?
That was my recollection.
Or real practice?
But wasn't this was a post-station, right? The fact that they got the 20 days earlier was then explained after they saw it.
Oh, is that?
That's my recollection.
Okay.
I might be wrong. I was asking.
I'm not 100% sure.
Well, it would be a prediction that we have independent measurement of A.
Yeah, that's true.
Otherwise,
yeah, no, I think it was a justification.
I thought they had post-Newtonian applications before that. That's why I thought it was so yeah. And then after, so let's say the black holes merge, what happens to the gas surrounding? There have been many studies investigating the response of the disk to this merger event. So when you have two black holes merge, you have burst of radiation that extracts energy from the system, and so the disk responds to that loss of mass essentially in the system. And so that's a mass loss effect. Eventually, gravitational waves could dissipate into the disk. That's less likely. There are kicks observed in black hole mergers, and those kicks can then bring a portion of the disk with it as it's expelled from its surroundings. And also, once the circumbinary disk that surrounds the binary right before merger is torqued up by the time varying quadrupole moment of the binary. And that creates a gap, and this gap then would refill after the merger that happens. So so you would see that the flux would evolve with an increase in temperature and in magnitude, and most of it, Infinity predicted that it would be observable out to a very large redshift, depending upon the mass of the through these X-ray telescopes that are so there are a few objects that are candidates for these kick disk objects. I won't go into it. I just want to highlight that this is an area that is being investigated and is interesting. But we're really interested in the pre-merger circumbinary disk. See if we can see a pre-merger signal from such an object. So what do we know about these disks so far? So here, Quadra et al. Simulated a self-gravitating disk and find that it leads to a much more elementary structure than a viscid hydrodynamic non-self-gravitating disk. And here they just take a binary equal mass. People have focused on, well, so the unequal mass where the mass ratio is around 100, maybe more astrophysically realistic. But to get I guess a handle on or a baseline on the physics involved, it may be easier to start with a mass ratio of 1. There are other practical reasons why we do that. Our gravity model is not well behaved when mass ratio is large. Numeric relativity codes are challenging at that mass ratio. The methods that we use become less accurate in that mass ratio. But there are other approximations that you can use in that regime, but for now we're going to be focusing on the equal mass binary. So, and these individuals also focused on the equal mass binary, and they find that, yes, the binary torques the gas that is falling into it, and it creates this gap. Okay, so there's very little material within the gap. The material that accretes from the outer portion of the disk piles up at the outer edge of the gap. And this gap tends to appear at around 2 times the separation. So I'll use A throughout the talk, and A is going to be the separation of the binary. So those were hydrodynamic simulations. Recently, Jermaine Shi, a graduate student of Jillian's, they looked at the magnetized disk. So we know that from accretion disk theory, if you have an ionized gas, then you're likely to have dynamically important magnetic fields. If you have dynamically important magnetic fields, then the magnetorotational instability will be the primary driver of angular momentum transport, and so that is what essentially mediates the gas accretion onto the central source. And so it's important that to include magnetic fields in these simulations, because local hydrodynamic viscosity doesn't accurately model angular momentum transport. So one key feature that they saw is that, so they did find a gap developed at around 2A. It is a little bit further out. And they did see more material exist within the gap. So the enhanced stresses from the magnetic fields allowed for more material to fall through that gap. So you had higher accretion rates onto the binary than you saw in hydrodynamic runs. But also you saw this n=1 structure for it. So this is, so if you take a turbulent distribution of gas, it'll have power at all scales of the domain, to very small, to the microscopic scales, all the way up to the macroscopic scale of the system. So it's not too surprising that MHD turbulent disks see power at n equals 1 mode, so the largest mode in the azimuthal direction. And so they find out this n equals 1 mode develops. Similar MHD simulations also see the n equals 1 mode develop. And what it does here in this case is that this lump accretes gas onto the binary, and more so than any other part along the azimuth. And so you get this buildup of gas in this lump, in this n equals 1 structure. So the question we want to explore is, as you shrink the binary, does the lump or does the gap follow the binary? At what radius does it decouple? Does the binary decouple from the disk? And these are all important questions to answer, because the luminosity is supposed to be sensitive to this decoupling radius, because that determines the thermodynamic content of the gas within the gap and the bulk of the disk. And so this is a order 1 correction to your predictions for what happens to the gas that falls onto the binary. So what we're going to be, we're kind of taking from a reference frame of Xi et al., and then we're going to shrink the binary. And in their runs, they excise the binary. So they neglected the gas accreting directly onto the black holes. They set boundary conditions that allow the gas to fall through this inner spherical domain, and they ignored all of the dynamics that happened within that. So we also followed that.
So you didn't take into account.
So they excise the binary at this radius, and
I mean, if you have a mass ratio that's different in unity, right, then you could, in principle, have some gas orbiting the more massive black hole inside the orbit of the less massive black hole.
Right.
And people, of course, consider the finding evolution of that system as the black holes merged together. And so I wonder, this is parenthetically, has such a non-equal mass ratio been studied numerically to see whether the gas actually appears in such orbits?
The gas appears within the separation? Yes, yeah. Yeah, gas has, as we saw in the planetary discussion earlier today, we see gas accrete onto the binary. So this has rich circumbinary disks have a rich history in the protoplanetary literature, and also it shows black holes. But also,
well, I guess what I'm asking is, in the planet case, you have extreme mass ratio.
Right. But you mean in the marginally extreme? So like,
well, say mass ratio of 3 to 1 or something like that.
Okay.
10 to 1.
Yeah.
Would you have an inner disk as well?
Yes. Actually, in Newtonian regime separations, you would expect that each individual black hole, even in the equal mass space, would have their own accretion disks. So that the accretion rate is fast enough that that the inner disk wouldn't disappear before more gas came out of power. So that's another interesting thing that we'd like to explore in the future when we remove that excision region, is how do those disks interact? Especially with magnetic fields, it would be really interesting to see if the couple and stuff not revealed that.
And in this simulation, what is the vertical aspect ratio? Because
In channels, I believe it's 0.05. Our disk thickness is 0.1. So we want to, so we're coming from the Newtonian regime. We're now in the post-Newtonian regime. Ultimately, we want to get into the dynamical GR regime. And some people have are already doing this there using simpler matter models. The first group studied particles orbiting a binary and show that as the binary progressed, you get a hotter gas of particles essentially. So they measured the Lorentz factors for particles. They also people also looked at binaries immersed in a hot cloud of gas and studied the evolution of the accretion rate onto the individual black holes and the luminosity using a posterior calculation for luminosity. These are hydrodynamic, so non-magnetized. Aristotle did a similar thing. I won't get into the technical details. They see variability if in the accretion rates and luminosity based on the fact that there's some differential motion between the black holes and some flow. So if you're going upwind with each individual black hole is going against the flow, then you create these shocks that then lead to bright features. And these variable signals are on the time scale of the binary period. And they give estimates of the synchrotron mission of that of an AGN. It's not too surprising. Any sort of accretion onto a central source that's efficiently radiating will give you an AGN luminosity. But in this case, it's 2, so maybe you'd expect maybe more, maybe brighter signals, as there's maybe more greater opportunity for dissipating energy, orbital energy into the disk through these torques. And so Aristotle started looking at disks as well as Bode et al. And they, so Bode et al. Took thick disks. Both were hydrodynamic, no cooling, inviscid, and they just rounded the binary with a disk that was very close to the binary, and they allowed the numerical viscosity to, it's not artificial, it's just grid scale viscosity to accrete material onto the black holes, and also the torque materials, and perturb the disk so that it would accrete material. And they explored the luminosity. So in Bode et al., they looked at the only the gas within the gap. They didn't consider the gap, the luminosity from the outer portion of the disk, and they measured variability on the orbital time scale because of light beaming effects. So they used an approximation to approximate the light beaming effect. And in Paris et al., you see that the disk follows linear Newtonian theory very well in terms of the torque and how the binary torque affects the disk. They also saw that these accretion streams form, and that they form ahead of the binary, each individual black hole. So the little accretion stream actually looks up, but there are these little accretion streams that come and attach to the black hole ahead of that black hole's orbit. And of course, Carlos did all this amazing work using binaries in electrovac and also in force-free plasmas, and these great jets coming from the black hole system. And they were very luminous, they were very bright, but at a low frequency, long wavelength, so we may not be able to see them with a typical telescope, maybe with Bowfar or something, but maybe that luminosity, that flux interacts with the plasma in some way and can give us light out there. So I'm sure you've heard Carlos talk about this. I need not go into it, but it's really spectacular work. And so, and we certainly like to see jets coming from our disks, from our black holes when we put our black holes on the domain. So where does our work fit in? So here's the GR regime. They've done some simple matter models with GR, full dynamic GR, and here they've done slightly more sophisticated matter models. She et al. Has MHD, and it's just a binary fixed orbit Newtonian binary. So we're in the middle somewhere. So we used sophisticated MHD techniques similar to the other numerical relativity groups. We have a cool disk that has a cooling function I'll go into later, so that the radiation predicted is consistent with the dynamical radiation losses. Yeah, that hasn't been done by others yet. So all the luminosity calculations from the numerical relativity codes calculate the luminosity based upon the simulation data, and didn't take into dynamical account of that loss of energy from the matter. So normally the radiation would cool the gas, and that could have a dynamical effect on the evolution.
The 2.5 doesn't include spin, right?
Excuse me?
The 2.5, yeah, doesn't include spin. The spin.
It can. We have non-spinning black holes in our system, but we're working on a 2.5 PN spinning framework with spinning black holes. But yeah, so we have non-spinning black holes. So the 2.5 PN, well, I'll go into it. So why do we need GR? GR changes the wave solutions in MHD. There's the transverse directions of velocity. 2SL interface changes the parallel directions as well. To the Lorentz factor, there are various technical reasons. So GR is important. Also, relativistic effects are important in creating the emission. You get light beaming effects that could drastically alter the variability, variable signal of the objects. And we need dynamic GR because the horizons change through the form. They also get closer, and there are going to be strong gravitational effects on the MHD, on the plasma, and also on the light coming out of it. So we hope to eventually get there soon. I first tried exploring this using the Einstein toolkit. And unfortunately, it doesn't have MHD fully implemented yet. We're working on it. The principal shortcoming is that this code doesn't scale incredibly well to more than 1,000 processors. So it restricts the resolution that we need that we can use on it. And it's also Cartesian. So disks are almost axisymmetric. So you want to kind of use a spherical domain to maximize your effort, so that it takes fewer cells to resolve a spherical disk than in the spherical coordinates than it takes if you use a Cartesian grid. And also, spherical grid allows you to conserve angular momentum more accurately. So we decided to use HARM and bootstrap the space-time onto it, or bootstrap HARM onto the space-time grid. I don't know which way it goes, but so HARM3 was written in a covariant way, so it was generic to the space-time choice, and so we just needed to alter a few things in the code to make it compatible with time-varying spacetime. It was originally designed to explore single black hole accretion disk systems, so we made it handle any sort of spacetime. And it's a pretty straightforward code, so it scales really well. It just uses block structured subdomains, so you just parcel out a volume of cells to different processors. And another advantage is that we've used it to study accreting systems a lot in the past. So we have a lot of analysis code that we can use to exploit the simulation that we get from it. For instance, there are two ray tracing codes. One's ray tracing, one's full Monte Carlo that are compatible with this simulation framework. But ultimately, we can't solve Einstein's equations with ARM. Yeah, I'm sure if we had plans to, but that's a shortcut. So we're using the post-Newtonian framework. And so the post-Newtonian framework that we're using is that of Eunice et al. And so essentially what you do is you use approximations to represent the spacetime in different zones. So there's a far zone, which is the wave zone. So it's Schwarzschild plus wave perturbations, or Kerr plus wave perturbations, or Minkowski plus wave perturbations. And then you get into an inner zone, so we only use then you get into the near zone. And we're only going to be considering the near zone in this calculation. And the near zone is, you're in the general vicinity of the binary, and that is 2.5 PN accurate, but you don't cover the space-time in the immediate vicinity of the black hole. That is handled by the inner zone, and those are matched Kerr or Schwarzschild metrics that are matched to the near zone space-time. So the patchwork area here are buffer zones in which those different approximations are kind of stitched together and interpolated together. So maintain a consistent level of accuracy over the whole body. And so I'll be talking about two runs. Run one in spirals, meaning that it starts at some fixed separation and then eventually gets very close together. So its separation shrinks, and that'll be indicated by gray lines in silver blocks. So here, and then run two, it's how that fixed separation forever. And the initial separation is 20 m. And our domain starts at 0.75 initial separation all the way to 13 times the separation to encompass the initial fixed star. So you see here, this is so at 40,000 m, m is the total mass of the black hole. 40,000 m, we let the binary in spiral. Okay, so the reason why we let it do that fixed separation is so that this relaxes from the initial conditions, so that we get some sort of, we start the in-spiral process after some equilibration phase, so that it's like a disk that we imagine would be in nature. So we use HARM, we use a typical configuration. It's in near hydrogen equilibrium, so it's pressure and it's in orbit around the black binary, and it's pressure supported and rotation supported. And we thread the torus with a magnetic field that follows density contours, and we use only one loop. So if you're familiar with this sort of method, and so so we start with a weak magnetic field. The shear of the velocity gradient strengthens the magnetic field, and eventually that and the MRI, the linear phase of the MRI, increases the magnitude of the strength of the magnetic field till it's dynamically informed and then enters a non-linear phase. And this is the surface density of run 2. So you see here, you can already see the equals 1 mode develop, and you see the info channels attached to each black hole. So this one, the binary doesn't shoot. I go into this later if you want, but essentially we use when it's at fixed separation, we start. So we want to start with a disk that doesn't include any numerical transients. So we want it to be in as close to equilibrium as possible. However, it's a time-varying space-time, so there's no true equilibrium. So what we do is we use a time average, which is just a phi average of the initial space-time, as our we assume that that's then a static space-time, and then we use this kind of prescription to generate the disk data. So these are tori and equilibrium in this kind of space-time, and our PN metric happens to have this form when you as mutually average it. So here I showed solid is the old method, dash is the new method, so there's less secular trend and less smaller amplitude of oscillation. So here's run 1, or run 2, when we keep the binary fixed. So this will run to 70,000. This is the surface density, so this is the density indicated height. This is the magnetic pressure, or twice or half the magnetic energy density, integrated in height.
Is this relative to the total energy density, thermal energy density, or is it cavity kind of minus 4 cavity?
These are in the same units. Yes. So surface density and magnetic density. So the rest mass energy density is usually much greater than the magnetic.
Oh,
Also,
sure,
we get it,
sure.
You would find a forestry disk, which doesn't exist.
But not explaining what the beta of the disk is.
Beta. Okay, yeah. So I didn't plot the pressure here, unfortunately. Beta. I have plots at the end of the extra slides that I can show you.
But typically it involves
well, so there's no steady state of the system because there's time-varying space-time. There's secular evolution of these quantities, and we see beta increase. It actually starts off at around 1 and increases past 10 in the bulk of this. That has to do with the lump. So maybe it'll make more sense.
So it reaches near 1 in the inner part.
Yes. Yeah, it starts off fairly.
Due to the molecular process.
Yes, and the torquing of the binary on the gas enhances the shear of the magnetic field, and also the nonlinear development of that line. So here's the flux integrated in height 2, and this is the accretion rate, so where you are. And so these are all in the plane. So the binary is in the plane of the disk, and so these are all coplanar images. These are the color scales. This one, and this one are on log scales, and this one is on linear scale. So you see that you see these accretion streams form, and so there's negative accretion rate, so there's accretion onto the binary. But then those streams then are flung out, they're torqued by the binary, and some of the material is flung outward. So here, this is if you see this dark red feature, this is the lump that forms. And you see these strong modulation of the accretion rate as materials flung into this lump. And this is also where a lot of the energy is dissipated. So the flings out material, the steepens from shocks, and also collides with the lump that's there. And then that mechanical energy is dissipated and heats up gas, and then that is radiated. So we're using a cooling function that is supposed to maintain a constant entropy from the initial state. So that means that we're radiating any dissipation that happens from the turbulence or from the binary torques. And so that's supposed to gauge the local emission rate in our disk. And so that means that our the luminosity figures that we get at the end are dynamically consistent with our simulation. We're not double billing the simulation with our luminosity estimates. This is run 1 where the binary shrinks. I started this right around the time in which the binary started shrinking. And if you pay attention, you can see the black holes actually get closer, and you see, wait about this craziness. This is a gauge effect. And because it's where you are, it's not it's a technical detail. But all the scalars are along there. And so you see that there's enhanced dissipation as it increases up to a point. And then that's when the disk essentially decouples from the binary. And so that's an interesting thing. Lots of movies. I like showing movies because that's one reason why I'm in this game is for the movies. So I hope I didn't show too many movies down here. But so we see this lump form. So it forms over time. It grows slowly, and the growth. Actually, it took longer in our simulation to form these lumps than it did in CITA. We're not sure why, but they see a similar lump structure. And the torque density, so the dashed curve is the linear theory from Newtonian physics. And we see that the wavelength of it is much shorter than so our wavelength of the oscillations are longer than the Newtonian theory, and that's consistent with what she et al. Said sees too. So we have fair agreement between the two simulations. Also, our torque curves look surprisingly similar. We start with different initial conditions. So this one difference is the magnitude. So we have to scale. We're at 0.68 times the linear theory estimate, whereas she et al. is at a quarter of that. So there's amplitude shift, but we find that actually this amplitude grows secularly over time, so we may be in a different regime of the correlation. So if you look at this at a space-time plot, torque density, so this is R in units of the initial separation, so this is run 2 and this is run 1. Okay, so here the binary shrinks, the torque density follows the binary as it shrinks. I'm going to now transform it into R units of A of t, and you see that it actually follows binary very well, except that the torque density diminishes in strength right at the very end. So yes.
You must have some outward dynamic flux including the flux, just due to the thermal magnetic torques.
Yeah.
How does that compare magnitude with the, so you calculate this torque by this asymmetric mass distribution, and you just do Newton on this?
Well, it's a relativistic.
It's relative.
But yeah, sure. Well, it's hard to measure the amount of angular momentum being transferred outward because, well, no. But you can, yes.
It looks like you have a large aspect ratio of radius.
Right. So here, this is essentially what I've shown here. This is the gradient of the angular momentum in radius of time. And the green line is the Reynolds stress, or the gradient of the Reynolds stress. Blue is the torque, red is the magnetic stress, and black is the total. And so the black shows deviation from a steady state. And so you see that there's this buildup of matter near the gap. So it's, it's building of material. The material is orbiting, and so it has to be in it. And here's just the magnetic stress, the Reynolds stress, and the total stress over gas density. So this gives you the alpha factor. So it increases with decreasing radius. I'm running out of time, so surface density also follows the Inspiral, but not as fast. And so there's some decoupling at some radius, and that radius is consistent with the level of alpha that we measure and also the thickness. So the standard calculation gives uses an alpha that is pretty small. It's much smaller than we see in MHD simulations. So if you use the thickness that we use and the alpha that we measure, the separation radius or decoupling radius is around 11 m. And this is essentially the point at which we see decoupling happen too. So this is the luminosity profile radius. Run 1 is gray, run 2 is black, and then here this is the surface density. So you see that the torques creating these ripples that are transmitted to a larger radius and are dissipated and create these peaks in the luminosity. So you see up until around 50,000 m that the profiles were fairly consistent with each other, even though the binary had been inspiraling for 10,000 m. So at 50,000 m, the binary separation was at around, I think, around 12 to 13 m, coming from separation of 20 m. So accretion rate, we saw a dip at 40 m that continued in run 1 as the binary recedes from the lump. It's obvious that it's gonna, as the boundary is moving inward, its relative velocity with the accretion flow or decreases, and so you kind of run away from the flow. So that's why it's somewhat, but it's still comparable to what we see in R2. Luminosity. So also similarly, the luminosity profiles are similar. So note that 0 is not on the y-axis here. So even at the very end, it's only a factor of 2 down from the non-spiraling case. And the profile of the luminosity in R follows that of a regular disk up until the lump, where a lot of the dissipation is happening from the torque. And so the picture that we're forming is that there's a regular accretion disk outside, and then there's an enhancement of the luminosity right around the location of the lump. And that there is some finite luminosity within the gap, but it's not large compared to that here at the lump. And the luminosity that we get, if you use an optical depth from a typical AGN, then you get astrophysically interesting, cosmologically interesting luminosities of that of typical AGN. So if you stay 1,000 into this equation here, you get 10 to the 43 ergs per second, which is close to great zone levels. And the temperature that you get from the thermal spectrum would be UV, so it would be brightest in the UV. So I wanted to look at, so the luminosity also follows in spiral. We want to look at the variability. Is there a signal? So this window, this space time diagram, so you see these obvious oscillations. Window it, you remove the linear fit to it, you get this trend. So this here, the right hand side I have average and radius. This is radius, which is time. Take an FFT, you see a bright spot form with a frequency of 1.47 megabit, which is the curious number. And it's not 1.5, it's not 2, it's not 1. So where does it come from? It's a close-up picture. So this is on a linear scale now, and so you can see it has very small size in this plane. And so the green curve, this is the Keplerian frequency of the orbit at the radius of the lump. But this is at a much higher frequency, and so in order to figure out what the origin of this is, we took the FFT of the variability of the surface density peak, and we found that they matched pretty well. And so it must have something to do with the surface density. So as we saw in previous slides, that the luminosity follows those waves that form in the surface density. So it's got to be there. So precisely how, what's the origin of that frequency? Right? Why is it 1.47 instead of just a 1.47 times omega bin. Why isn't it frequency of the binary? And so here is a movie of the surface density in the and the movie is co-rotating with the lump, or approximately co-rotating with the lump. And so you see that the lump doesn't move in this frame, of course, in angle much, but that it there are these decretion streams that are kicked out by the binary torque and are dissipated at the lump, and so it's twice the frequency at which that happens is twice the beat of the frequency of the binary and also the frequency of the lump, because it's equal mass, so it happens twice in the same way, right, for every period of the binary orbit. Now, if they were unequal masses, then like let's consider a mass ratio of 1 to 1,000, then you would have a primary surrounded by a secondary, and the secondary would be beating this lump. And so it would just be omega bin. It would just be the beat frequency between omega bin and the rotational frequency of the lump. And so as the mass ratio goes from 0 to 1, this frequency of emission would be from the frequency of the variability of the emission would go from 1 to 2. So if you measured, so let's say it's put on our imaginary hats and say, okay, this is what we're going to see. Then if you see a variability at this rate, and you know, then you know something about the mass ratio. Will we be able to see this variability? Well, it's essentially obfuscated somewhat by the opacity of the disk. So these things are going to be very opaque, and as I said, the optical depth could be order of 1,000, and so that the optical depth acts as a low-pass filter for this variability. And it will be, the amplitude of variability will be diminished by this factor, and it depends on for instance, the alpha value of the disk. So this value ranges from 0.16 to 0.32 with this value of alpha over this mass ratio range, because it's also a function of omega. So we've made, in conclusion, we've made connection with prior results in the Newtonian regime. So we believe what we're doing is right, and we've identified several properties of the disk that follow the Inspiral, and we see that the disk does not decouple, or may not decouple from the binary until very close to the, until very small separations, and so there's likely to be lots of material near the binary as it merges, and so this increases the likelihood of seeing these things at large distances, because there will be more material to dissipate the energy into and give a brighter signal. We've also identified variability in our luminosity model, and this may or may not be detectable, but it does connect the orbital dynamics of the binary to the light that we see. So that's the good news. So in the future, we want to include the black holes on the domain to study the interesting effects, disk effects, and also the jet effects from the system. And also explore spins, because spins, if they're unaligned, the orbit will precess, and that will also greatly affect the dynamics of the jet, or the lump in the future. So that would alter probably the value of omega peak that we calculated. And so I'll just end there. Thank you.
Are there any questions?
Do you want the data file? Because this is log data. And this is a slice
How does that compare with a similar disk around a single block?
It's similar. You don't see, so you see beta usually stay above 1 in the bulk. Here it's becoming much larger than 1 because in the lump, the reason why you would ultimately stop these simulations is because in the lump, the magnetic field drops. And when the magnetic field strength drops, you're not resolving the growth, the fastest growing mode of the magnetorotational stability, and so you're not accurately modeling the system any longer. And so it's kind of like a dead zone in some conditions. So that's why you're seeing an increase in data because the magnetic field strength is dropping really long.
Now, the question about the angular flux is that you think that in the quite steady state, the torque in the binary has to be equal to the outward flux underlying the risk that the sonic nerve effectively around, presumably where the orbit becomes strongly non-circular.
Right, yeah, we do see that the Reynolds stress and the magnetic field stress balance the binary flux. So, yeah, okay.
And what's the effective radius where that balance?
It's within the gap.
Within the gap. So you have this dashed line you're drawing.
Right, which is around 2.5 times the separation. So this plot shows. Okay, so in order to get the black curve, which drops to 0, you sum up all of the color curves. So what that means is that since the black curve is 0 here, that means that so the gold is the effective angular momentum. Okay, green is a Reynolds and red is the magnetic field. So the sum of all of these. So here, since the effective is 0, we know that the Reynolds plus magnetic stress balance binary torque energy.
I have a question of if you try with different resolutions and see what these results depends on the resolution of
That's a very good question. We didn't do a formal convergence study of these results, but we based the resolution of this run on previous experiments. So we did do hydro disk evolutions in the plane of the binary, and we did a resolution study in that run to see that we're resolving the spiral density features that we see, and so we're well within the regime that does resolve the spiral density features. Also, we made sure that, I'm sorry, I was going forward to have a plot demonstrating our MRI resolution. So we do also demonstrate, so there are various quality factors that you can measure that give you confidence that you're at a point in the convergence that has okay, so there have been studies that found that as you increase resolution, you reach this point at which the saturated magnetic field strength remains fairly level. Okay, so and there are these quality factors that you can measure. So it's essentially measuring how many MRI wavelengths are you resolving in different dimensions. Okay, so here I'm showing you the quality factor in. So this is this is for the vertical magnetic field, and this is for the azimuthal magnetic field. So this is the number of cells per MRI wavelength, and we find that, and these are the criteria that Hawley et al. Found that yielded reasonable resolution of the MRI. And we find that most of the disk, for most of the time, is very well resolved, except for a portion within the lump at late times. And then it becomes mediocrely, moderately resolved. So, and since it agrees well with the Newtonian calculations, which were done with more cells, but with a lower resolution scheme, so maybe it's comparable resolution of those facts give us confidence. These runs are kind of expensive. Run one took about 500,000 to 600,000 SUs. So it's hard to do a significant precision study.
Okay, well, Scott is going to stay until tomorrow afternoon, I think. He's in the digital office. If you want to talk to him, we'll link him tonight for him. And we can continue the discussion with something.